Now we are going to learn how the hydrogen spectrum that could be viewed with the help of the experimental setup. Here the hydrogen gas that is filled up within the gas discharge tube. The hydrogen gas atoms which are filled up within the discharge tube, they could be excited with the help of electricity, that is due to electric discharge. The excited hydrogen atoms, they are capable of emitting the four visible spectral lines, that is red, bluish green, blue, violet. Four visible spectral lines are emitted from the excited hydrogen atoms. Here the plane diffraction grating is used to observe the visible spectrum of the hydrogen atom.
Lines of the hydrogen spectrum. A transition from the third orbit to the second orbit emits red light at a wavelength of 656 nanometers. A transition from the fourth orbit to the second orbit emits blue-green light at a wavelength of 486 nanometers. Jumping from the fifth orbit to the second orbit emits blue-violet light at a wavelength of 434 nanometers. And finally, a jump from the sixth orbit to the second orbit emits violet light at a wavelength of 410 nanometers. Notice that as the energy of the transition increases, the wavelength of the emitted light
Now we are going to learn how the spectral lines are emitted from the atom. Look at here, let us take hydrogen atom. In the case of hydrogen atom, the electron that is revolving in the first orbit. When it is revolving in the first orbit, it is said to be, it is in the ground state. Here, the same electron, it is drawn here. If you draw this kind of diagram, they are all called as energy level diagrams. The same electron that is drawn here, it is in the ground state. Let us imagine the principal quantum number n is equal to 1. The energy of the electron in the ground state is to be taken as E1. If sufficient amount of energy is given from externally, that is in the form of heat or in the form of light, so if energy is given, it will absorb the energy. Are you clear? It will absorb the energy. The electron, it will absorb the external energy, and after absorbing the energy, the electron, that one will be excited. Are you clear? So it will reach the excited state. This is a normal ground state, this is the excited state. After absorbing the energy, the electron is switched to, that is excited to the higher level. There, the electron, it won't be there for a long time. There it will be residing for some time. So the time taken to reside there in the excited state is called lifetime. The lifetime will be very small. There it will be existing for very short duration of time. After a certain duration of time, the excited electron, that one will come back to the ground level. Are you clear? While it is coming back, when it falls to the ground level, here the energy is emitted. That energy emission, that one will be taking place in the form of photon. So the energy is emitted in the form of photon. So the energy radiation that is emitted in the form of photon. That photon that is in the form of waveform. Okay. So it is having wavelength and frequency. So when it comes out, that one will appear in the form of spectral line. Depends on the energy difference, the wavelength or frequency of the emitted spectral line can be calculated. From Bohr's postulate, we can write it as the difference in energy. Look at that, very important formula. E2 minus E1. The difference in energy, that one will appear in the form of the emission of photon, that is the emission of the spectral line. So the energy of the emitted photon or the energy of the spectral line, that can be calculated as h nu. So E2 minus E1 is equal to h nu. This formula is given by one of the Bohr postulates. If you want to calculate the frequency of the emitted spectral line, we can use the formula nu is equal to E2 minus E1 divided by h. So by using this expression, we are able to calculate the frequency of the spectral line. Are you clear? This one will appear in the form of line spectrum. If it is caught on the photograph, you can get it in the form of spectral line. That one will be in the form of line emission spectrum. If you want to calculate the wavelength of the spectral line, here we have to do a simple modification. E2 minus E1 is equal to h. Instead of nu, we can substitute c by lambda. Therefrom, we are able to get the expression for lambda. Lambda is equal to hc divided by E2 minus E1. So by using this expression, we are able to calculate the wavelength of the emitted spectral line. This is a very fundamental formula. In the next topic, I am going to teach you about how the spectral lines are emitted in the case of hydrogen atom. Here h is the Planck's constant, c is the speed of the light, E2 minus E1 is the energy difference between the two successive lines, energy levels, where the electron transition takes place. Very important formula to calculate the wavelength. Okay. Now we are going to see how the spectral lines are emitted in the case of hydrogen atom. Look at here. Here I have drawn the hydrogen atom, in which you have to imagine that the electron, it is already in the excited state. When the electron, when it comes back to the normal level, by the time the spectral lines are emitted. Let's see the transition here. Now the electron, it is in the third orbit. When it is coming back to the second orbit, it emits a spectral line. I am going to calculate the wavelength of the spectral line. That spectral line, that one will be in the in red in color. Okay. So the emitted spectral line, that one will be in red in color. All the spectral lines are visible. So here I have drawn the energy level diagram. As I have told earlier, the electron transition that takes place from the higher energy level n is equal to 3 to n is equal to 2. So when it is coming back to this level, clearly it emits the spectral line. That emitted spectral line, it is having wavelength. How will you calculate? What is the formula? E3, energy difference must be calculated. E3 minus E2 is equal to, what is the energy value of the third orbit? Look at that here, minus 1.51 electron volt minus this one, minus of 3.4 electron volt. Here after subtraction, already I have calculated everything. The difference is 1.89 electron volt. Okay. So from Bohr postulate, this one can be equated with what is this? H nu. H nu is the energy of the emitted spectral line. Okay. Emitted photon. So here this H nu can be equated with this one. Energy difference is this one. This E3 minus E2 can be written as H nu. So therefore H nu is equal to 1.89 electron volt. We are going to calculate the wavelength. Hc by lambda is the formula. 1.89 electron volt. Here lambda is required. Lambda is equal to, cross multiply this, Hc divided by 1.89. That electron volt value is there. That electron volt value must be converted into joule. That is very important. 6.6 into 10 to the power of minus 34 into 3 into 10 to the power of 8 speed of the light whole divided by 1.89 into this one to be converted into joule, no, therefore 1.6 into 10 to the power of minus 19. So after calculation, after simplification, the final answer will be 6.547 into 10 to the power of minus 7 meter. If it is converted into Armstrong, you will get 6547 Armstrong unit. This one can be written as 10 to the power of minus 10 meter. After conversion, the value of wavelength of the spectral line, that can be obtained in terms of Armstrong. Okay, so this is the wavelength of the emitted spectral line. If you find out whose wavelength it is, if you find out from the spectral chart, it shows that the spectral line will be clear in red in color. Are you clear? So the emitted spectral line will be red in color. Okay. Now we are going to see the emission of the next spectral line when the electron falls down from 4th orbit to 2nd orbit. When the transition takes place from 4th orbit to the 2nd orbit, another spectral line will be emitted. That one will be in bluish green in color, bluish green color. Okay. How to calculate the wavelength? Look at that. Here, the transition that takes place from the 4th energy level, 4th orbit to which orbit? 2nd orbit. Now another spectral line will be emitted, its wavelength to be calculated. Already I have given the formula for wavelength. The formula is lambda is equal to, again and again we need not write, otherwise I will calculate. E4 minus E2 is equal to E4. The energy of the 4th orbit is how much? 0.85 electron volt minus of minus 3.4 electron volt. The energy difference will be 2.55 electron volt. Which one is equal to h nu? That is the energy of the emitted photon. So the energy difference is equal to, energy difference between these two levels is equal to energy of the emitted photon. So h nu is equal to energy difference. So h nu is equal to 2.55 electron volt. This one could be modified as hc by lambda is equal to 2.55 electron volt. Here our aim is to get the wavelength of the spectral line. Lambda is equal to, here cross multiply this. How will you get? hc divided by 2.55 electron volt can be written hc divided by 2.55 into, here that electron volt value must be converted into joule, 1.6 into 10 to the power of minus 19. H into C, both of them must be substituted. 6.6 into 10 to the power of minus 34, 3 into 10 to the power of 8 whole divided by this 2. Is it clear? 2.55 into 1.6 into 10 to the power of minus 19. If all values are calculated, finally you will be getting 4.852. 4.582 into 10 to the power of minus 7 you will get. After displacing the decimal point, you will get 4582 into 10 to the power of minus 10 meter. This one could be written as 4582 Armstrong unit. If you observe if you go through the spectral line chart, therefore it is found that the color, the emitted color will be in bluish green region. This color is called bluish green. The spectral line will be in the form of bluish green. Okay. Look at the value of the wavelength. It is in the form of bluish green. Okay. Now we are going to see the third transition and the third spectral line which is emitted from the hydrogen atom. Here look at the third transition. The electron, excited electron, it is falling from 5th orbit to 2nd orbit. The transition that takes place from 5th orbit to 2nd orbit. So by the time one spectral line is emitted, now we will see what will be the wavelength of the emitted spectral line. Look at here, the electron transition that takes place from 5th to 2nd. How to calculate the wavelength? As usual, is it clear? We have to write the formula E5, energy of the 5th orbit minus energy of the 2nd orbit is equal to, energy of the 5th orbit is minus 0.54 electron volt minus 3.4 minus 3.4 electron volt. So after that, after subtraction, you will get the answer as 2.856. 2.856 electron volt is the energy difference between these two. The emitted photon, that one will have this much amount of energy. So which is equivalent to the energy of the emitted photon. Energy of the emitted photon can be calculated by the formula h nu. Therefore, the energy of the emitted photon can be calculated by calculating the energy difference between this and this. So therefore, h nu is equal to 2.856 electron volt. That is the energy difference, that is the energy of the emitted photon. Now we are going to calculate the wavelength of the spectral line, h c by lambda, which is equal to 2.856. Here the electron volt must be converted into joule, 1.6 into 10 to the power of minus 19 joule. Okay, how to calculate the wavelength? Wavelength is equal to, cross multiply this, hc divided by 2.856 into 1.6 into 10 to the power of minus 19 joule. So here the value of h is, that is Planck's constant and velocity of the light, both of them must be substituted. 6.6 into 10 to the power of minus 34 into 3 into 10 to the power of 8 whole divided by this value, 2.856 into 1.6 into 10 to the power of minus 19. If the calculation is done with the help of calculator, you will be getting 4.332 into 10 to the power of minus 7 you will get. Are you clear? If this one is converted into some other value in terms of Armstrong, the decimal point to be shifted. Okay, so 4332 into 10 to the power of minus 10 meter. Okay, this is equal to how much? 4332 Armstrong unit. If you look at the spectral line chart, the wavelength chart, therefrom we could find out that the emitted line will be blue in color. Are you clear? Blue color light is emitted when the transition takes place from 5th orbit to 2nd orbit. Okay. Now we are going to see the last case. We are going to see the emission of the last spectral line. This is also visible. So here look at that. Here the transition that takes place from 6th orbit to 2nd orbit. 6th orbit to 2nd orbit. The electron, it falls from 6th orbit to 2nd orbit. By that time also one spectral line is emitted. Are you clear? That one will be in violet in color. Are you clear? So when the transition takes place, that one emits the violet color photon. Now we are going to calculate the wavelength of the emitted photon. How will you calculate? Look at the energy level diagram. The transition electron moves from 6th orbit to 2nd orbit. Now how will you calculate? The formula is E6 minus E2. Energy of the 6th orbit minus energy of the 2nd orbit. Substitute the value, minus 0.377 electron volt minus of minus, which one? This one, minus 3.4 electron volt. After calculating the difference, you are getting 3.023. 3.023 electron volt is the difference, energy difference value between this level and this level. This is equal to the energy of the emitted photon. The photon which is emitted now, its energy is equivalent to this much. Now this two can be written here. H nu is equal to 3.023 electron volt. This one could be converted into joule. 3.023 into 10 to the power of here 1.6 into 10 to the power of minus 19 must be multiplied. After that we are going to calculate the wavelength. How will you calculate the wavelength? hc by lambda, which is equal to this value, 3.023 into 1.6 into 10 to the power of minus 19. So how to calculate the wavelength here? here wavelength, that value to be cross multiplied. Lambda is equal to Planck's constant value, Hc, 6.6 into 10 to the power of minus 34 into 3 into 10 to the power of 8 whole divided by this value to be cross multiplied. 3.023 into 1.6 into 10 to the power of minus 19. So after calculation, finally you are getting the answer is 4.099. 4.099 into 10 to the power of minus 7 meter. If it is converted into Armstrong, you will get 4099 into 10 to the power of minus 10 meter, which is equal to 4099 Armstrong unit. So if you look at the spectral line and wavelength chart, there we have found that the color of the spectral line will be in the form of violet in color. Are you clear? Very important one. I would like to mention on about the another thing here. This is called visible spectrum. 4 spectral lines are emitted now. All the 4 spectral lines, they can be caught on the screen and you can see them directly, and it can be taken in the form of photograph. These spectral lines are combinedly called as Balmer series. Okay, in the case of hydrogen, some invisible radiations are also emitted and visible radiations are also emitted. Now, the visible region of the spectral line is combinedly called as Balmer series. Are you clear?